As I promised, we're going to start in a fairly simple way. Namely, we're going to start by defining what the determinant of a 2 by 2 matrix is. This is very simple. It's actually the starting point even historically, and so it's going to take me a few seconds, just a very few seconds to explain it to you. So the determinant of a 2 by 2 matrix is obtained as follows. You take the elements of the main diagonal, multiply them together, take the elements of the other diagonal, multiply them together and subtract. Okay, so this is basically what the determinant of a 2 by 2 matrix is. It's just a cross product of the main diagonal minus the other diagonal, and that's it. All right, now the question of course is it useful? Remember, we want to construct a single number that has some usefulness. Well, it turns out it's fairly easy to see that these properties occur. For instance, we can prove, and we're going to do that in class, that that a matrix, a 2 by 2 matrix, is invertible if and only if its determinant is not 0. Which means, by the way, that most matrices are invertible, right? Because this determinant can be any real number, but only those for which the determinant is 0 are going to be non-invertible. And this of course implies that a linear system of the form ax equals c has a unique solution if and only if the determinant of a is not equal to 0. So as you can tell, the information contained in this determinant already starts to have some impact on the character or the matrix and its properties. So this looks like a good definition. In fact, it is. So what we want to do is we want to try and maintain that. So how we're going to extend this? Now this is a very simple procedure, but notice that it depends very strongly on the fact that we have a 2 by 2 matrix. Once we go even to a 3 by 3, which diagonals are we going to multiply together and how we're going to include the other numbers? Let's see how that is done. So here is the smart idea we're going to use. Instead of defining the determinant through some kind of complicated algebraic formula like it was done traditionally, we're going to analyze some of the properties of the determinant of a 2 by 2 and see if we can extend that one. What are these properties? First of all, we're going to look at the effect of row operations on the determinant of a 2 by 2. So for instance, notice that if we switch two rows, then let's say we're taking, oh, by the way, when you're computing when you're writing down the determinant of a matrix and you're writing down the matrix in terms of its components or its elements, notice that we drop the square brackets. Okay, so the determinant of a matrix A can be written with just the two vertical bars and its elements inside. Now this is done of course to avoid having all kinds of brackets one inside the other and so on. So it's just a little aside. Alright, so let's go back to our point here. So if we switch two rows, we start from the matrix that has that determinant and we switch to this new matrix which will have this different determinant. You may want to check the algebra here. And if you compare the original one to the new one, you'll notice that the new one is actually the opposite of the original one. So what happens is switching two rows has the effect of changing the sign of the determinant. Keep this in mind because this is going to be very important later. The second type of row operation is multiplying a row by a non-zero scalar. Again, here is the algebra. Multiply, let's say, the first row by k. The result is basically going to be the same determinant we had before, all multiplied by k. And you can check on your own that if you multiply the second row, you get exactly the same answer. So multiplying one row by a scalar, non-zero, because of course that's the row operation we do, it has the effect of multiplying the whole determinant by that same scalar. Finally, if we add to a row a multiple of another row, let's see what we get. Well, again, let's add to the second row a multiple of the first one. If you do the algebra, you may want to pause and check it. This is the expression you get. Now notice that we have a KAB and a minus KAB, which of course we can delete. And so we're left simply with AD minus BC, which amazingly enough is exactly the same determinant that we had from the original matrix. Okay, so that means that adding to a row a multiple of another row does not change the determinant, which turns out to be quite convenient. Alright, now we're going to look at two more properties of this determinant for 2 by 2, and then we're going to put it all together for the determinant of a larger matrix. So here is another interesting property of the determinant for a 2 by 2. If we look at a 2 by 2 which is in REF form, then its determinant uses only the main diagonal. And that's kind of obvious, because if it's in REF form, that means that the lower left element has to be 0. That's the only condition, right? But that means that all we're left with is AD minus 0, and therefore if we're in REF form, all we have to do is multiply the elements on the diagonal. The other thing is also that the products, remember I mentioned that we wanted products to be preserved? Well, it turns out that this is true for 2 by 2 matrices, so that the determinant of a product A times B is going to be equal to the determinant of A times the determinant of B. Okay, here we're running into the first little glitch. Not so much a glitch, this is perfectly true. But if you try to prove it, even for a 2 by 2 matrix, is going to be quite an exercise. I strongly encourage you to do it. You should be able to do it at least one, or you should do it at least once, so you can tell your grandchildren, once I checked that that property was true. But you're going to see that even in this kind of very simple situation, the calculations and the algebra, all the letters involved become very complicated. Okay, so again, if you want, you can check proofs in some other book or publication, but you should check it on your own. It's really not that complicated. Okay. So now what we're going to do is we're going to put the properties coming from row operations and these two properties about REFs and products to come up with the definition of the determinant for a larger matrix.